you the only day that we're going to just take some notes. All right. Most days we're going to have a calculator and we're going to be talking about math the whole time. And this will take about a week and a half to do the topic of the gas laws. And then the rest of the semester is largely a mix of math and theory. There's no strictly just math or just theory. Now, kinetic molecular theory, and I'm going to abbreviate that KMT and all of the remaining notes that we have, just because I got lazy and didn't want to keep typing that. But KMT stands for kinetic molecular theory. Now, you guys have all heard the word kinetic in science classes for years. Kinetic means what? Moving, motion, right? So it's just the idea that particles in a sample of matter are always in motion. What's wrong, Devin? You what? Oh, you need to find it because you need it for a third period when you go to the career expo. They told us all to make sure y'all have pencils when you go because you have an assignment.
So are we having a junior meeting?
I don't know. My kids asked me that yesterday in both classes. I have no idea. I would have thought.
Jumped over us. Like they did seniors and then they did sophomores.
I heard they weren't going to do juniors. I heard they weren't.
I have no idea. They don't usually tell us. I don't know.
What happens if we don't do this? Harness us for the career.
I have no idea.
Isn't that thing that they do every year? Yeah.
As long as it takes matter.
I can virtually assure you my third period class will not do the assignment. We will go to the gym. They will wander aimlessly. They will not do the assignment.
I'm not either. I have enough to say.
All right. Now, whether we're talking about gases, solids, or liquids, all particles have motion. Now, because we're specifically talking about gases at the moment, gases, go ahead and close it. It won't close on its own. You got to turn the door on. All right. So we're going to turn the door on. All right.
You can still hear it. It's so annoying.
Well, I can't fix it. Gases have all three types of motion. This is actually something we talked about with bonding. So this could be on the test tomorrow. All right. All gases can vibrate, meaning their particles can vibrate. They can translate. So when you get up and leave here to go to third period, y'all are going to translate. Most of you don't shake really bad, so you're not going to vibrate. And perhaps some of you have the ability to rotate. I certainly do not. All right, but some of y'all might have that ability. I guess if I laid on the floor, I might be able to. Now, I think, talked about this earlier in the semester, that motion stops at absolute zero. Now, what did we define absolute zero as? Anybody know? Or am I just dreaming that we talked about it? Did we talk about it?
I don't think you told us the number.
Okay. Anybody know?
One.
Absolute zero is defined as 0 Kelvin.
Yeah, we did.
We didn't talk about that? Okay. Because I teach it in 2 classes, I'm never sure where I put it when. All right. Motion stops at absolute zero. Absolute zero is defined as 0 Kelvin, and I probably have it under the screen. 0 Kelvin, yep, I do, is actually negative 273 degrees Celsius. Or, to put it on a Fahrenheit scale, because most of us are used to that, is negative 457 degrees Fahrenheit. Now, even if we think about the coldest day we had this winter, which was probably around 8 or 9 degrees Fahrenheit, when we drug ourselves in here for school, and you guys all pissed and moaned about, oh my God, Ms. Wall, it's so cold out there. I can't believe they made us come in and didn't give us a 2-hour delay. All right?
They'll like get us out of school the next day.
It was still almost 500 degrees warmer than absolute zero. Okay? So, what am I trying to tell you? I mean the particles in your desk right now. Are they moving or are they stationary? They're moving. The particles in your shoes, in your pencils, are moving. In the floor, in the cement walls, are doing what? Moving.
So
When you're dead, what are the particles doing? They're moving.
So what would happen if they were to stop?
We'd be at absolute zero.
What's,
What would happen?
Nothing. It's a theoretical number. We've not reached it yet.
So what would happen?
Everything will stop moving. Now, the closest example I can give you is if you've watched things like Bill Nye Science Guy, and you've seen him put stuff in like liquid hydrogen or liquid nitrogen or liquid oxygen. And let's say he takes a banana and he drops it in there, he pulls it out with the pliers and he uses it in a hammer or like a tennis ball. And he puts it in there, he pulls it out, and he throws it on the floor and it shatters. That's the closest I can give you to an example of absolute zero.
what temperature is that?
Pretty cold, but still not an absolute zero. All right?
It's in the -100, so.
Yeah. But it's still not an absolute zero. Okay? So, everything is moving. So, now, I point this out because I'm going to ask you on the test, and people are going to get this question wrong. Okay? It's a lot like yesterday. My daughter had a test at West. Let me see if I can get the question right in my head. The question said, which does not affect population growth? Okay? Y'all all had our science and biology. Which does not affect population growth? Birth rate, death rate, immigration, and Chuck Norris. What's the answer to the question? You know who got it wrong? Some argue it was immigration. All right. Now, I'm telling you that this question is on the test. And which one do you think people are going to argue with me about? They are. They're going to tell me that which two states have motion. And they're going to tell me solids don't on the test. I don't know why, but every year I get this test, and every year I do not get 100% on this test question. And not only do we put it on this test, we put it on the next test because the next topic is going to study solids and liquids. And we don't manage to get 100% on either test. Okay? So, let's see if we can do it this year. Now, you do not need to write that. These were sub notes that I did. Now, we're going to talk about ideal gases because we're a first year chemistry class, and ideal gases are a nice launching point into studying gas laws. Now, for those of you who may one day study chemistry or pursue a fancy science degree, you will study ideal and real gases. But if you only have to have a very low-level chemistry class because you're going into a nursing degree program, you will probably only ever study ideal gases. However, for those of us who are just getting a chemistry class because we need it on our transcript because we want to go to a 4-year school, we are only studying ideal gases. Now, an ideal gas essentially has to obey the 5 assumptions of kinetic molecular theory. I think that's all I have on that slide. It is. So, what are these 5 assumptions? Well, these 5 assumptions are the things that are going to make our gas seem pretty close to what we can get in nature. And they're pretty easy to do. All right, has everybody got what they need? Everybody have what they need? Everybody caught up? All right, so number 1, all gases are going to have a large number of particles. All right, so for example, if we work a word problem that has 1 mole, let's see what we remember. How many particles are in 1 mole? Very good. Very good. All right. If we had a problem that had 1 mole in it, we would have this number of particles. That would be a giant number of particles. Okay? So, it's not hard to have a large number of particles in our sample. We're not going to work any kind of problems that have 2 atoms or 2 molecules. Okay? We're going to work problems that have a large number of particles. That's pretty easy. We can do that without much difficulty. Now, we're going to assume that all gases move in straight lines. Generally speaking, they do. Gases do not have brain cells. They don't look up and go, oh, there's Hiero. Let me go around it. Oh, there's Tevin. Let me curve. Walk around it. They tend to be like people on the main hall. I don't care if they're in the way. I'm just going to bump into them and shove them out of my way. All right? Oh, you found your pencil? Oh, good. Glad to hear it. All right. This board and I are not getting along today. Number 3. All collisions are elastic. This is a new vocabulary word for us. Elastic. And I do not mean elastic like your spandex or underwear.
Flexible.
In this case, no, it does not. Okay? I mean that there's no loss of kinetic energy. I mean it's transferred. Now, this is the one thing that really separates us from being a real gas. In reality, does all of the energy get transferred from one gas molecule to the other? No. Some of it would be lost to friction as heat and be lost to the surrounding area. So when one gas molecule slams into another gas molecule, we're assuming that every bit of kinetic energy this one has, it is all given to this gas molecule, okay? None of it is lost to heat or any kind of friction or lost to the environment in any way. Does that actually happen? No. Typically, in a real world situation, you are going to lose some of the energy to the surrounding area. There's no way to avoid that. But we're going to assume that none of that happens. Okay? Because that would really complicate our math process. All right, number 3. There are no attraction or repulsive forces. All right, to do that, we're just going to use nonpolar molecules because those are the weakest types of attractions. Okay? Not a problem. We'll just pick nonpolar molecules. It's not hard to do. We're going to have attractive forces that are incredibly weak, so we'll just pick nonpolar molecules. And the last thing is kinetic energy depends on temperature. So, if we increase temperature, what happens to the kinetic energy? Does the kinetic energy increase or decrease? It increases. Okay? Anytime we increase temperature, kinetic energy will increase. The particles are going to move faster. Everybody with me? What? I'm sorry. Why? All right, is everyone caught up? Okay. And when you have it, Dustin. All right, everybody there now?
No.
Who said no? Sure. All right, so what conditions are going to give us an ideal gas? I just told you one here. What are we going to use so that we get an ideal gas? What did I tell you on this page that we can do to get an ideal gas? What kind of molecules did I tell you we were going to use?
Non-polar.
There you go. So we're going to use non-polar molecules. Now, we want these molecules to move in straight lines and not attract each other. So do we want them to be at a high temperature or a low temperature? All right, I hear low, I hear high, I hear low, I hear high. Just because I don't answer immediately doesn't mean y'all have the wrong or the right answer. Stop just back and forth, back and forth. Think about it logically. Do you want the particles to be close together if you don't want them to attract or repel each other? If the temperature is low, do they move fast or slow? Slow. So if they're moving slow, are they likely to attract and repel, or are they likely not to? Think about it.
We'll see.
If they're moving fast, are they likely to have time to attract each other or not? If they're moving really fast, for example, have you ever played with magnets before? All right. So if the magnets are moving really slow when you're playing with them, do they have time to attract or repel each other? But if you're moving really fast, do they have time to attract or repel? No. So would you want a high temperature on the molecules or a low temperature? A high temperature, okay? Now, think about pressure in the same way. If you want them not to attract each other, do you want the molecules close together or far apart? If you push them together with high pressure, they're going to do what? They're going to attract each other, right? But if you keep them separated with low pressure so they're far apart, they're less likely to attract. So do you want them to have a high pressure, pushing them together, or do you want them to have a low pressure, keeping them far apart? A low pressure. Okay? So the reason for these two things is it keeps the molecules far apart. So when we work our math problems or our formulas, we will just have math problems where, generally speaking, the temperatures are at least going to be at room temperature and the pressures will be at least at atmospheric pressure in this room. We won't work problems where the pressure is very low, very low. That's how we'll meet the guidelines of the ideal gas law. Okay? MOLC is molecules, right? MOLE is moles. Now, what is a real gas? All right? Hello, Tejan. All right? You need me or you just pass it through? We're not offering any science AP classes next year.
Do you teach any of this?
Do I? No. Haven't in years.
In this case, I am just asking.
Okay. So, what is a real gas? All right. A real gas is a gas that what? Does not obey the 5 assumptions. A real gas does not obey the 5 assumptions. These are the ones that actually exist in nature. So, given we're not going to use these, what kind of gases will you see in the word problems? You're going to see things like our diatomics. These are a lot of the types of gases you're going to see. Now, one of the reasons that Leandra said some people dislike the gas laws is when we calculate, people tend to forget the diatomics. So when we need the masses, people look up chlorine and they go, oh, its mass is 35.4. But it's diatomic. So what do you have to do to the 35.4? Times it by 2, and people forget that all the time. Or oxygen, and they go, oh, it's 16. And they're supposed to remember that they have to multiply it by 2 and get 32. Okay? So there are little things that cause people issues with that as we cruise through the unit. Questions? Yep, I can.
Do we have to write those ideal gases?
They're just examples. I don't care what you're writing, your notes. All right, everybody have what they need? All right, so the last thing we need to do today are the 5 properties of gases, and then we're good to go. All right, a lot of this should be reviewed. All right, most of us have seen all of these words before in other science classes. None of this should be new. Everybody should know that gases have the ability to expand to fill their containers. Get off the phone, Tim. Now, I know you weren't on your phone. I was a figment of my imagination. Now, do liquids or solids have the ability to expand? I get that a lot. Now, if liquids have the ability to expand, will my soft drink regenerate itself between now and lunchtime? No. It'd be super fabulous if that would happen, even though Leandra keeps telling me to stop drinking my Pepsi. All right? Is it going to regenerate itself and fill itself back up by lunchtime? No. Y'all's water bottles would automatically refill themselves without having to go out there and refill it at the water fountain, if it did. That does not happen. Okay? If something expands, when you put it at the bottom of the container, it will automatically fill to the top of the container on its own spontaneously without you having to do anything. Okay? So only gases have the ability to do that. Now, gases can be compressed. That's a fancy science word there to help that definition. You can squish it into a smaller space due to space between the molecules. Now, at some point in your science background, somebody, hopefully, drew a picture for you of a gas that had gas molecules maybe spaced out like that. And there's a whole bunch of empty space between the gas molecules. So, when you consider all that empty space, we can do what to a gas? Well, all these particles can be pushed closer together towards the center, and they can be compressed, which is what happens. Who was it yesterday that asked me about CO2 in the canisters? Was it you, Tevin? Asked me about carbon dioxide? Somebody did. And we talked about the fact that for like soft drinks, we compress it and we fill it up in a pressurized tank so it lasts longer.
I thought we were talking about soda though.
We were.
Yeah.
So like for soft drinks, even though we exhale CO2, we can compress that and put it in a tank so that they can keep it for longer periods of time. They don't have to show up every day to refill carbon dioxide tanks at restaurants and like gas stations. As a matter of fact, sometimes if it's a newer gas station, they'll even have like an outside spout on the side of the building that will say CO2, And big trucks could just back up to it, hook a hose up to it, and refill it from inside the building. They don't even have a canister. It's just a connection or a fitting that hooks to the side of it, and a truck can just back up to it, hook the hose to it, and fill the tank. Instead, you know how soft drinks used to have those big cans, they had to offload the cans and take them in, they connect to, so, y'all probably don't remember. Never mind.
Something like McDonald's.
It's the carbon dioxide, they run out. There's two parts, it depends on the machine. Once upon a time, it used to come all mixed together, the carbonation and the syrup was together. But some machines now are separate. You have the syrup and you have the carbonation, and it mixes in the machine.
Yes.
Which is why I was saying now, the newer ones, they have an outside line and the truck just backs up and hooks the thing to it. So that it's separate.
That's what we got our restaurant, like at the syrup, or our fancy tanks outside.
Yeah,
And I think somebody can like hook it up.
yep,
I think that's good. I mean, it's like a really big tank.
Yeah. And they just refill the CO2 tank. So you can compress all of that and keep the CO2 stored in the tank, and you can keep more of it that way. Yeah, but when the CO2 runs out, then you just have to syrup. That's what it's flat. Yeah. Yeah, but the old way they did it is they had tanks that were probably about this tall and about this big around, and they had handles, and you had to drag the tanks everywhere. They had two handles again, screw them on.
So it's almost like cakes.
It was a lot like kegs, and you have to have the kegs in the bag, and take the kegs out, put the new kegs in, and they all had different lines, so with different stouts and machines, and they were all the little kegs under the cabinet, and you have to unwind and take them out, and put new keg skins to the new line.
Oh, yeah, they're like serving that.
The old ones would sit in the back, and then the drink company would come pick old kegs up, bring new kegs in, and they'd have to have storage space to store all that, yeah. And all the syrup, you know, your hands were all sticky, it was nice. Yeah. But they've got a better system for that now. All right, number 3. Gases have the lowest density of all 3 states. All right, why do gases have the lowest density? All right, think about math. If you have density equals mass over volume, volume has the biggest number on the bottom, right? What happens if you have the biggest number down here? That's right. Yeah, we did too. All right, so if you have the biggest number on the bottom or in the denominator, when you divide, you get a small density. That's just basic math class. Y'all learned that way back probably in elementary school.
Density on it.
No, you just learned that if the big number is on the bottom in the denominator, when you divide, you get a decimal number, right? You get a little number.
Yeah.
That's why gases have the small density, because they have a big volume. They take up a lot of space. Now, gases are fluids. They're able to flow. The molecules move around you. When you get up to leaving at 11:40, you're going to walk through the air. The gas molecules are going to flow around your body, and you're going to walk easily to third period. If you tried to walk through the wall, do the molecules move and flow around you? No, I can move the table. All right? If I try to walk through this door, though, I'm not going any farther. The molecules are not going to move around my body, no matter how big I am. And then the last one, diffusion. It's the spontaneous mixing of 2 or more materials. Right now, that fish tank back there, woo, it's ripe.
One more week.
I know, thank God. All right, well, every time we go back there towards the copy machine, the smell sort of collects at the copy machine. Unfortunately, there's no getting around it. Those fish are out of here. We cannot avoid the smell. It is the spontaneous movement. One of the reasons teachers get bent out of shape when students pass gas in class is, does the smell stay right there behind your behind? No. It spreads. Okay? If you're a cologne or a perfume kind of girl or boy, and you spray it back there where Alicia's at, and I have sensitive Smell tendencies. Does the cologne and the perfume stay back there with her?
No.
No. Diffusion spreads the love to everybody. Okay? Question. What is our homework tonight? No, it is to study. You choose. Okay? Now, the only thing I would tell you, for those of you who are like, Ms. Wall said I have test corrections. There are 80 questions on the test. Hush. They are 1.1 something, or essentially 1.2 points each. So in order to make a difference on the test corrections, you have to do what? A lot of test corrections to affect your grade. So if you only come and do like 4 test corrections, is it going to help your grade at all? No.
It's gonna be test questions on that one, right?
Huh? Yes, that's what I'm telling you. But you have to do a lot of test corrections for it to be beneficial, because there